Hello and welcome to this video about classifying chemical reactions. Chemical reactions can be classified based on how atoms are rearranged. And you might have noticed there are all sorts of different chemical reactions, millions occurring every day, and we have a few different categories that we like to use to help us sort of categorize how different atoms are being rearranged. So we're going to look at combustion reactions, synthesis, decomposition, single displacement and double displacement, and oxidation reduction reactions. Combustion reactions. Well, everyone's pretty familiar with these. A combustion reaction occurs when a substance or substances react with oxygen and they produce energy in the form of heat and light. An example of a combustion reaction is shown right here. Flames of heat and light are produced when carbon in the wood reacts with oxygen in the air and forms carbon dioxide and water. A synthesis reaction is when we have simple materials and we're forming a more complex compound. Two or more substances are combining, in other words, to form another substances. This is the general formula. We have two simple substances. It's making something more complex. Synthesis. Here are a whole bunch of examples. And notice the synthesis of water here. We have hydrogen and oxygen forming something more complex, water. This is also a combustion reaction because it produces flames in the presence of oxygen. Again, this is a synthesis and it's a combustion reaction. So reactions can be fit in more than one category. Carbon and oxygen produces carbon dioxide, and in the presence of oxygen, this also produces a flame. Now we can have something that is the opposite of synthesis, where we have decomposition. We have this more complex substance breaking down into its substituent components, or decomposing. It's the very opposite of synthesis, and here are some examples. The decomposition of hydrogen peroxide in the presence of light produces water and oxygen. That's why your hydrogen peroxide comes in a very dark bottle, because when it's exposed to light, this process occurs faster of breaking down into water and oxygen. Now let's look at these displacement reactions. We have single displacement and double displacement. And here is the general formula for single displacement. We have a single element by itself, in this case zinc, just one atom of it. It's going to react with this molecule. In this case, the molecule has two atoms in it, hydrogen and chlorine. It's hydrochloric acid. And that is going to be rearranged in such a way that this atom will combine with one of the atoms in the compound, and then the other atom will be kicked out and left on its own. You can see how that happens right there. So in this case, we end up with hydrogen being the single atom, and in this case, hydrogen is diatomic, so it ends up being two hydrogen atoms together. And then we have zinc chloride as the molecule. In a double displacement reaction, we have two molecules, two compounds that are going to be rearranged. The cation is going to combine with the anion of the other compound. So in essence, you're going to have the two cations switching places. And you can see that in this example right here. The potassium is going to combine with the nitrate over here. And the iodine is going to combine with the lead iodide. One important thing to notice in this equation right here, we have potassium iodide aqueous. It's dissolved in water. This is aqueous also, and so is this, aqueous. But look at the lead iodide over here. It's a solid. Another word for this type of solid that forms during a reaction is a precipitate. A precipitate is an insoluble compound, and it comes out of solution. And if you think of this as this reaction is taking place, this will form a cloudy or murky substance, a solid, that ends up settling to the bottom of your little beaker in the reaction, and it's called a precipitate. Now let's take a look at an oxidation reduction reaction. An oxidation reduction reaction, although it sounds like it has a lot to do with oxygen, the thing it has to do with is electrons and the transfer of electrons. Oftentimes these are called redox reactions because this whole big long phrase takes a long time to say. And it is only when electrons are transferred that we can classify something as an oxidation reduction reaction. Right here is an oxidation reduction reaction because it involves the transfer of electrons. How do we know electrons are being transferred? Well, remember our oxidation states that we assign to different species in a chemical reaction? Let's do that right now. Oxygen here is going to have a charge of 0 because it is in a perfectly covalent bond where the electrons are being equally shared and it is not gaining anyone's electrons. If you look at the periodic table, you can see that oxygen wants to gain 2 electrons, but it can't gain 2 electrons from just another oxygen. It's sharing equally. So the oxidation state here is 0. Iron is just sitting there. It is not in a bond. It is not an ion. It has an oxidation state of 0. Any atom or elemental molecule is going to have an oxidation state of 0. When we look at iron oxide over here, we can see that oxygen here is going to have a charge of -2 because it is in a bond with this iron. Iron is going to have some plus charge we can figure out, or we can just simply stop here and say, whoa, electrons are being transferred because oxygen right here has a charge of 0, and over here it has a charge of -2. It gained electrons. Oxygen is being reduced because it's gaining electrons. I know that sounds intuitively opposite what you might think, but because it's gaining a negative charge, it's being reduced. Now let's just for fun figure out the oxidation state of iron. We can see that we have 3 oxygens here, each at a -2 charge. That gives us a total charge right here of -6. -2 times 3 is -6. We need a positive 6 charge over here for all of these irons so that we can have our neutral compound. How are we going to do that? We have 2 irons, so we need to distribute the positive 6 charge between the 2 irons. It means each of the irons will have a +3 charge. So this is actually called iron 3 oxide because iron, remember we put the 3 in Roman numerals for the +3 charge on this cation. Iron's going to be a +3. And this is so interesting. You knew this anyway without having to figure that out, but iron is losing electrons because it is going from a neutral 0 charge to a positive charge. That means it's getting rid of electrons or it's being oxidized. In this case, the iron is being oxidized because it is the one that is losing 1 or more electrons, 3 electrons in fact. An easy way to spot a redox reaction is there one side of the equation or the other that has elemental molecules or individual atoms on them where their charges are 0. Because if there are, and on the other side of the chemical equation, either as the reactants or the products, there are compounds, you will have an oxidation reduction reaction because electrons are being transferred in those cases. Advanced ideas. A lot of the single displacement reactions involve oxidation and reduction. Can you look at some examples? Explain which substances are being reduced and which are being oxidized in a single displacement reaction. Some other types of reactions, acid-base, precipitation reactions. What are the defining characteristics of these types of reactions? Choose a type of reaction and come up with a list of examples. And how are some of your examples useful or interesting? So I look forward to seeing what you come up with, and we'll see you in class.